I'm Jeff Wagner, a developer for CELPP. In this video, I'll show an example of how to implement your contestant server using CELPPade. CELPPade is just one option for participating in CELPP. It's a bunch of template functions for handling our weekly challenge. You're free to make your own end-to-end solution without it, or just use the parts of it that you want. CELPPade is modular, so you can just pick and choose pieces as you like. The first thing to do is figure out what your prediction process looks like when you run it manually on the command line. Assume that we start with two files, receptor.pdb and ligand.smi. The example that I'll show today is a more complicated case. There's a good chance that your implementation will be simpler than this, but here I'm trying to cover some more exotic problems that folks may run into. The receptor is a single chain from the PDB. That includes non-protein atoms, and ligand.smi contains a smile string of a ligand that we'll be docking. The program that I'm implementing today is called rdoc. rdoc requires a 3D ligand SD file as input, so here we perform simple, cheap conformer generation using rdkit. The receptor.pdb file is straight from the PDB. So it might contain waters, other organic solvents, or entire ligands. Different docking programs can handle these in different ways, but for the sake of simplicity, I'm just going to strip those all out. This is a really simple script that just removes every line that doesn't begin with atom. It will get rid of waters, other solvent molecules, as well as connect records or other information lines. rdoc requires charges to be calculated for all the receptor atoms. Here, we just reuse Chimera's docprep tool and run it with all default values. Again, this code will go up online, so you can reuse and tweak it as you see fit. Like a lot of docking programs, rbdoc requires a grid generation step. In this case, the input for the grid generation is a parameter file. While I'll use generic parameters for the grid generation, we will need to update the grid center each time. I'll show you how to generate the yellow highlighted file later on in Python. Here's the docking command. doc.prm is a built-in file that comes with rbdoc, so we don't need to generate that. At present, CELPP only wants your single best guess. So while rdoc generated 50 potential ligand poses, we're going to sort the output to put the best scoring molecule first. Now we'll use the open source conversion program Babel to take the first molecule from the file, convert it to mol, and name it properly. If you want CELPPade to handle your result packaging and uploading, you'll need to have a step to change your output files to have the proper name. And here, we follow the naming requirements with the receptor. In this case, we can safely take the clean receptor file as the final confirmation, because we didn't perform flexible docking. If your program does move the receptor around, you'll want to copy that final confirmation as your docReceptor.pdb file. Now I'll discuss how we'll shape these commands to fit in the CELPPade template. When you download CELPPade, you'll get a bunch of template classes split over a few main files. I'll start with what to do to make a minimal implementation of your contestant server. This won't be efficient or easy to modify in the future, but it will get the job done now. For a minimal implementation, ignore all of the template functions except for doc in the doc.py file. Just plan to have all your commands run under the doc function, and that's it. Here are all the commands from before, just put under the doc function. But what I'll show in this video is the most proper implementation, where we'll split our steps into the appropriate spots in the template. Here are all of the functions that can be overwritten. Colors indicate different files. Splitting your method into independent ligand preparation, receptor preparation, and docking steps really unlocks this entire field of modular prediction solutions, where people can share their code and mix and match these steps in an effort to win the contest. This gives more focused method developers a way to get recognized for what they do really well, without having to worry so much about steps in the prediction process that they don't specialize in. You should not change the first and last files, get challenge data and pack docking results. These are uploaders and downloaders, and if the contest changes format or moves to a different platform in the future, we'll take care of putting new versions of these up on pip, and we'll notify the community to do a pip update. We split molecule preparation into two steps. The first step, scientific preparation, is basically processes that add information and might be useful for somebody else's implementation. Examples of things that fall into this category include missing atom replacement, protonation, charge calculation, and decisions about handling non-protein atoms in the structure. The second step is technical preparation. This is bundled into the same file as your docking function, and should just have the really specific steps that deal with your docking method. Examples include things like grid generation, file format conversion, and proprietary atom typing. You'll notice that the candidate prepared and ligand prepared file suffixes have been filled in. We found that it doesn't make a lot of sense to heavily regulate file formats between scientific and technical preparation. So we encourage scientific preparation steps to make as many file formats as possible, and we require the technical preparation steps to specify what file type they expect, by making them define a file suffix to pull in from the scientific preparation folder. And finally, we put the docking commands into the dock function. Again, we don't want to get too restrictive with file formatting, so the technical preparation steps pass on a list of file names that will be copied into the docking folder. Also, note that we didn't define a ligand technical preparation step here, so the template code will just pass along ligandprepared.sdf and a list into the dock function. Now we'll start talking about the software side of CELPP. Since CELPP is a weekly process that will probably run in the background of my computer, I'm going to implement my contestant server using Miniconda. This way, my CELPP contestant server is isolated from other changes in my system. These commands will create a minimal Python build in your current directory. Note that Conda enables us to install the latest version of RDKit directly. And I do recommend that you do this, as the RDKit is continuously finding and fixing bugs. We use Cookie Cutter to distribute the CELPPade template. This provides everyone with a GitHub-ready structure for their contestant server. It will ask some questions when you run the Cookie Cutter command, but these don't report back to us or anybody else. They're just filling in fields for the files you're downloading, and preparing a GitHub-friendly structure for you if you do decide to use online version control. Once Cookie Cutter is done with its prompts, you'll have a new folder in the current directory. This folder contains some test data, but we'll get to that later. For now, we'll look into the main code. Here, we find the three files. Protein prep has the receptor scientific prep function and output suffix definition. This super command is just telling the function to fall back on its template, which would happen even if we completely deleted the function from this file. But we leave it in here so users have a correct function definition ready to go if they want to change it. The ligand scientific prep file is similar. Again, the suffix definition and a super call. The doc file has three functions for overwriting. These are the receptor and ligand technical prep steps, and of course the docking function itself. I've skipped ahead to when I've implemented my RDoc steps into the CELPPade template. I'll walk through how I did it, and we'll do that by looking at before and after shots of these functions. In the protein prep function, we first let CELPPade know that our main output is going to be mol2. At the end of protein prep, CELPPade will check to make sure that this file exists and has non-zero size. Like I said, you're encouraged to generate other formats, but CELPPade won't consider the preparation successful unless this specific file exists. I removed the supercalls. That's because we are overriding the default behavior of these functions with our own code. To emulate my receptor cleaning command, which ran a simple Python line filtering program, I just copied the lines from that program straight into this function. The second command is a little bit more difficult to implement in Python. It requires Chimera to be running and to have it read this Python script using its own interpreter. We solve this problem using a sort of Python inception by here putting the special Chimera Python code into a string, writing that string to a file, and then having Python start Chimera in a shell. Notice that the output file of this process is set to be named according to the prepared protein file string. Because we specified the mol2 format as our main output, we are guaranteed that this file name will end in mol2. Ligand preparation for RDoc isn't too bad. I've just taken the code from my original Python script and put it straight into this function. It starts by reading the smile string from the input file and then using a couple RDKit functions to generate a 3D model. Notice that when the program writes out, it assumes that the output file will have an SD suffix. Again, this is guaranteed because we've specified the output lig suffix variable to be SDF above. In doc, we specify that we need a mol2 file for the receptor from the scientific preparation, and an SDF for the ligand. Now we have to write two functions, receptor technical prep and doc. Remember that the ligand is good to go as SDF, so we are not going to overwrite the ligand technical prep function. Let's look at receptor technical prep, which for RDoc is grid generation. The big issue here is that for different targets, we need to define a different grid center and input file name in the PRM file. Conveniently, these two items get passed in as an input to the receptor technical prep function. So here, we're just defining a template for what a vanilla PRM file looks like and replacing the parts that are relevant to the system. This function writes out the PRM file and then runs a grid generation program. Now, we define which file should be copied forward into the docking folder. RDoc is interesting in that it requires both the grid file itself as well as the grid generation PRM file for the docking step. But that's alright, we just add those to the list of return values, and those all get passed along to the doc function. Remember that we'll need to send out a receptor confirmation at the end, so I'm bringing the mol2 file along as well. Now let's look at the doc function. First, we unpack the technical prep results. This will be the same list as was output by the technical prep step. Since we did not implement the ligand technical prep function, that input is just whatever was carried over from scientific prep. In this case, the ligand prepared.sdf file. For clarity, I'm unpacking the variables individually here. Next, we run the docking command, sort the output poses by score, and extract the highest scoring pose into the properly named mol file. This file name again is passed in as a parameter to the function. That's our final docked ligand pose. Then we do the same for the protein, converting the mol2 back to PDB to act as our output receptor. It usually takes me a few tries to get a new program running. CELPPade includes a miniature challenge tarball that allows you to test your code as if it were running a real week. To test my build, I'll go into the test data folder and run test.sh. I'm fast forwarding here because it takes a few minutes, but this script will run each of the steps that we just made in a different folder, so you can use it to track down bugs. It's especially helpful to have piped standard error and standard out into files here for debugging. If everything went well, all the steps will have run, and pack docking results will have collected all of the successful predictions for submission. Since this is a fake week challenge tarball, the week and year strings are all replaced with X's, and so is your contestant ID. Without an FTP config file containing your login credentials, Pack docking results doesn't upload anything. But we can open up these results in PyMol and check visually if our predictions look reasonable. And actually, since this is pretty old data, we can check out how we did against the actual PDB structure. Cool, it looks like we did pretty well on this target. Now I'll talk about how to join the contest and how to submit your predictions. Check out our wiki page at github.com/drugdata/d3r/wiki and select the Participate in the Challenge link. Once you have followed the instructions on this page, you will have created a box.com user account and received an email with your CELPP contestant ID. Even if you already have a box.com account, we recommend that you make a separate one for the contest, as CELPPade's automatic submission tool will require a plain text file containing your box.com username and password. To enable automated uploading of your weekly results, you'll put your CELPP contestant ID and box.com login information into the FTP config file that came with the cookie cutter package. The FTP config file will contain your box.com password in plain text, so you may want to move it outside of your Git file tree, or ensure that it doesn't get version controlled with the other files. The test and full week run command sequences are nearly identical, except for the first and last steps. You should use a task scheduler to run the full week run script at the beginning of the weekly challenge cycle. Note that the existing data will be deleted each time the script is run. If you want to keep the previous week's data, be sure to copy those results into a separate directory. The full week run code downloads from our challenge data folder on Box, and at the end uploads to your CELPP contestant submission folder. Thanks for taking the time to learn about CELPP. We're excited to open up this contest to the public. For more information, head over to the project wiki and watch the Drug Design Data Twitter for updates.